The early Earth before life began. After the solar system formed, what happened on Earth so life could begin? In the beginning God created the heaven and the earth. And the earth was without form, and void, and darkness was upon the face of the deep. Genesis 1:1. Whilst this planet has gone cycling on according to the fixed law of gravity, from so simple a beginning endless forms most beautiful and most wonderful have been, and are being, evolved. See Darwin. Hello, could someone turn on the light? Dude, Earth without form. In both human and planetary births, the parent's context is critical to the health and survival of the offspring. For example, if our sun was born in a stellar nursery with a nearby supergiant star, fierce stellar winds from such a big hot star would have driven away the dust and gas, the raw materials of planet formation surrounding our infant sun. Instead, our small, calm sun was born in a quiet corner of the galaxy, and the Earth was born along with its protective bigger siblings in the solar system. The Earth, in its turn, was fruitful and multiplied, and produced life. We'll explore some of the early Earth's context and how that affected the origin of life. The pillars of creation. The Eagle Nebula, Hubble telescope. The sun first ignited about 4.65 billion years ago and quickly burned away most of the gas and dust, the elemental products of stellar furnaces, leaving a compact protoplanetary disk around it. The first solar system solids condensed quickly from that disk about 4.57 billion years ago and then rapidly evolved into a bumper car ride of planetsimals, asteroids between a 1-1000 kilometers, and protoplanets greater than 1000 kilometers, all crashing into each other. The big ones grew bigger fastest by gravity, quickly clearing out the disk, and soon the inner solar system of terrestrial planets developed: Mercury, Venus, Earth, and Mars. Protoplanetary disk AS-209 in the Ophiuchus star-forming region ALMA. The Grand Tack, about 4.56 billion years ago, still in the early phases of planetary development, a Mars-sized protoplanet crashed into the young Earth and vaporized much of the surface materials in both. The vapor cloud continued to orbit around the molten core of Earth, and eventually coalesced into two bodies, the Moon and Earth, each with identical surface chemistries, and matching orbital and rotational periods. There was no water on these two bodies at this time, since the asteroids that formed them were baked dry by their proximity to the Sun. The Earth and Moon remained molten for about 30 million years before continental crusts finally solidified. Then, Jupiter and Saturn migrated first in towards the Sun, then back out, a maneuver called the Grand Tack since it reminded astronomers of sailboats tacking. The Grand Tack disrupted the orbits of asteroids in the vicinity of the huge planets. The disrupted asteroids were farther away from the Sun, thus colder, and unlike asteroids closer to the Sun, were rich in water and organic materials. As those cold asteroids' orbits degraded, they plunged towards the Sun and some crash-landed life-essential materials into the rocky planets including Earth. This was the late heavy bombardment, around 4.4 billion years ago. The size and frequency of huge asteroid impacts during this bombardment occasionally vaporized the Earth's developing oceans. It took time once the heaviest of the collisions began to taper off for the oceans to reform and cool to near boiling temperatures. Zircon chemistry suggests that Earth had a crust with liquid water by about 4.3 billion years ago. There are no rocks from before that time to bear witness, as plate tectonics began about then and eventually erased almost all evidence. Zircons, tiny indestructible crystals of zirconium and silicon oxides that form as magma cools, are all that remain of those ancient rocks. But zircons are little time capsules that entrap within them hints of the environment in which they were born. The face of the deep, the addition of water to the dry molten Earth during the late heavy bombardment was the seed for many important developments in the geology and life of our planet. Water was essential not just for the formation of oceans and other surface waters. For example, the addition of water to solidifying magmas was required for continental crust to form. Water reacted with the lithosphere, the upper solid part of the Earth, to weaken it and initiate plate tectonics. During plate tectonics, water also lubricates the plates as they subduct, dive hundreds of kilometers down into the mantle. Water also helps rock to melt, which is key to volcanism near subduction zones. In fact, water has powerful effects on almost all aspects of geology, from the chemistry of the rocks, to their melt temperatures, to mechanical properties, etc. Where the ocean enters the Earth through faults, cracks in the crust, water penetrates far into the mantle and reacts with the hot silicate rocks there. Hot water is an excellent solvent, and in the depths of the mantle, water leaches out minerals, metals, and gases. The superheated chemical-laden water eventually works its way out through seafloor hydrothermal vents. Hydrothermal vents' rich chemistry, tremendous chemical and thermal energy, and plentiful catalytic surfaces make them ideal for synthesizing the various biochemicals necessary for life. The extreme depths and Hadine blackness of hydrothermal vents provide both challenges and advantages for the origin of life. The lack of sunlight, of UV radiation as an energy source, is a challenge to some theories of how life began. The lack of tides and a wet-dry cycle from the young moon similarly challenge some ideas of the cradle of life. But the kilometers of water above the vent also provided a buffer from the continued pummeling of asteroids and other assaults that may have occasionally sterilized early attempts at life near the surface. A dome in the midst of the waters, along with the hot new oceans, was a hot early atmosphere which was dominated by molecular nitrogen, N2, carbon dioxide, CO2, and smaller amounts of hydrogen, H2. Water vapor, H2O, was also a large part of this early atmosphere. This was not the easiest composition of gases with which to create the chemicals of life. If, instead, a reducing atmosphere of highly reactive gases had developed as imagined by the early origin of life theorists and experimenters, an atmosphere heavy in methane, ammonia, hydrogen, it would have been easier for organic chemistry. But it would not have lasted long. The hydrogen would have escaped into space after reacting with ultraviolet radiation pouring in from the sun and breaking down the ammonia and methane. No one's view of the early atmosphere had oxygen present at that time. Ideal chemicals for life to start, but not the likely in the early Earth's atmosphere. Illustration by ScienceJude. However, there was an overabundance of productive high-energy sources in the atmosphere, from lightning to ultraviolet radiation, traumatizing the molecules of gas to synthesize biochemicals. This synthesis happened in the atmosphere and even in clear water where UV energy penetrated to depths of about 10 meters. A few examples of experimentally generated amino acids from simulated early Earth atmospheres. These and others have also been found within meteorites. Illustration by ScienceJude. Hot springs on land, near volcanoes, were another source of life's chemicals. Ponds that can flood with hot chemical-rich waters one day, and dry out the next, drove a cycle of wet-dry chemical reactions needed to synthesize simple and complex biochemicals. A wet-dry cycle features in many theories of prebiotic synthesis, and here a hyperactive moon is often conjured. Some early models of moon formation had the moon closer to the Earth, causing extreme tides every 6 hours. The moon would have hovered over toxic skies, appearing twice the size of today since its orbit was half the radial distance. In addition to terrestrial chemistry, asteroids from the neighborhood of the gas giants delivered compounds essential to life onto the young Earth. Water, amino acids, nucleobases, sugars like ribose, fatty acids, and more. These are just some of the many ways that organic compounds essential for life accumulated on the early Earth. The ubiquity of water and of basic biochemicals throughout the universe, and particularly on various bodies throughout our solar system, suggests that the chemistry needed for life's precursors is not rare. In fact, some researchers propose that the early Earth was covered in a layer of organic compounds, a scum of oily residue that coated the water and the land, with perhaps a haze of organics polluting the air above. The question is not so much that there were organic compounds on the early Earth, but what specific conditions led to the abundance of those chemicals needed for life to arise. John D. Sutherland, a chemist at the Medical Research Council Laboratory of Molecular Biology in Cambridge, England, may have gotten the furthest so far in cobbling together a plausible set of reactions necessary for life to begin. In 2015, his lab was able to show that a common set of chemical steps could drive the formation of all the important biological molecules, ribonucleotides, amino acids, and lipids from simple precursor chemicals such as hydrogen cyanide, powered by UV light. The opening line of his February 2020 paper in Science Advances is probably at least as important as a strategy and call to action, as the technical information he reviews in that paper. We advocate an integrative approach between laboratory experiments in prebiotic chemistry and geologic, geochemical, and astrophysical observations to help assemble a robust chemical pathway to life that can be reproduced in the laboratory. An essential part of science is to experimentally verify the essential parts of a theory, and Sutherland correctly calls for an integration of the various and usually independent disciplines and groups. Without a theory being reproduced in the laboratory, All we have are opinionated people waving their arms. Experimental data and evidence, not opinions, is the heart of science, even one focused on what happened billions of years ago. Before life began. Thank you for watching.